So everything we're going to talk about today is joint work with my PhD student Hegor from Georgia Tech and Caleb Patton, who's an undergraduate at Georgia Tech. And the theme of the talk is that we want to study a certain graph theoretic parameter for random graphs. And so here, the parameter that we want to look at is the so-called Prague dimension. And so, as in many areas of mathematics, some notion of dimension often plays an important role. And in the late 1970s, in several papers by Neshetrel, Poulter, and Drödel, the so-called Prague dimension was developed. Okay, so the idea is somehow we need to define what is the simplest possible object. In this case, they decided on that being cliques. And then one way to define some dimension is to ask yourselves, okay, if I define some notion of product on these one-dimensional objects, in this case cliques, when can I embed or how many such cliques in the product do I need to take so I can embed a graph into the product of these one-dimensional cliques? This definition turns out to be maybe a little bit more complicated than I want to explain in this talk. The key point is the Prague dimension has several equivalent definitions, which in some sense shows that it's a very natural concept. And here I want to think of this in terms of clique edge coverings. Okay, so the idea is the following. So given some graph G, the Prague dimension of the complement of G is a little bit easier to define. So it's the minimum K, so that there is a clique edge covering of the edges of your graph G, which can be K colored. Okay, so you want to find, among all clique edge coverings, you want to find the smallest K, so you can K color such a clique edge covering. Okay, and here by coloring, I mean that if two cliques share a vertex, then they should receive different colors. Okay, let's maybe look at this a small example here. So this is here some small graph I've drawn with these edges, and so I've prepared here some clique colored clique covering. So this clique here is just an edge that will be green. This triangle will be green. This edge will be green, and then I've colored here this triangle, this edge orange, and these ones purple. So this is a valid three coloring of a clique edge covering of the edges. So this means in this case that the Prague dimension of the complement of G is at most 3. And so now you might ask yourselves, okay, is now the Prague dimension of this graph really 3? And one way to convince yourself is the following. Let's just look at this particular vertex here. So by construction, we know that cliques which intersect in a vertex have to receive different colors. So in this case here, we have this edge, and at least one edge or one triangle in every possible clique covering of this graph. So we need at least 3 colors, no matter which clique covering of this graph you generate, just simply because of the fact that this vertex will always be in at least 3 different such cliques. So in other words, this means here the Prague dimension of the complement of G is 3. Okay, and another way maybe to write this definition here in a more compact form is to use some notation here where we involve the chromatic index. So we can think about here that we take the minimum over all clique edge coverings of a graph G, and then we look at the chromatic index of this clique covering. So the idea here is that you can think of a clique covering just as a hypergraph with vertex set 1 up to n, and the edges of that auxiliary hypergraph correspond to the cliques in your edge covering. And so now when you color the cliques of your covering, that means just that you color the edges of this hypergraph. So in other words, you're just looking at the chromatic index of this hypergraph. So you can just think of it as you look at the minimum chromatic index over all possible clique coverings of your graph G. And just for notational convenience, instead of talking always about the complement of G, we can just say, okay, we just define some new property, in this case, say clique covering index, which equals to this quantity. Okay, so this is this notion of Prague dimension that we want to study. I want to point out that whenever there are any questions, please feel to ask them during the talk. So now we have this notion of Prague dimension. It turns out that in general, it's fair to say that this parameter is not so well understood for many graphs. So it's quite a natural paradigm to say, okay, let's try to understand how does this parameter behave on random graphs to get started, to get some idea maybe how does this parameter look like for almost all graphs or most graphs. And so here's a conjecture by Furedi and Cantor, which says that with high probability, with probability tending to 1 as the number of vertices tends to infinity, this Prague dimension of the random graph GNP, so it's the n vertex random graph where each of the n choose 2 edges is inserted independently with probability p. So their conjecture is that with high probability, the Prague dimension of the random graph GNP is of order n over log n for constant p. Okay, so here by order n over log n, here the implicit constants can depend on p. This is the convention I want to use here. And so using this notation here of this click covering index means that to prove this conjecture, it suffices to show here that this click covering index of GNP is of order n over log n with high probability. And the reason is that, well, as we saw up here, the Prague dimension I defined here with respect to the complement of G. So it means that if the Prague dimension of GNP corresponds to the click covering index of the complement of GNP, but the complement of GNP is very well behaved, right? So instead of inserting edge with probability P, we just think of an edge as being inserted with probability 1 minus P. So the point is that if you have some constant P between 0, 1, then also 1 minus P is some constant between 0, 1. So it's enough to show that this click covering index is of order n over log n. Okay, so let's try to see where does this conjecture actually come from. So as usual, in many cases, one of the directions is easy, the other one requires significantly more work. And so in this case, it turns out that the lower bound is easy. And it's a generalization of this observation that we made earlier about this graph, where we argued that, well, the Prague dimension or here of the complement is at least 3, because no matter which click covering you use, this vertex here will always be contained in at least 3 clicks. And so we can generalize that argument. The idea here is that let's just look at some vertex V here, which say is of maximum degree of your graph. So in other words, it has here delta many neighbors. And suppose that now our graph has maximum clicks of size omega. Okay, so what that means now is that no matter which click covering you look at, right, any possible click that you select into your click covering can cover at most omega minus 1 vertices over here in the neighborhood of V, right? Because together with this vertex, this would form a click of size omega. Okay, so every click of size omega here can be can eat up at most omega minus 1 vertices in the neighborhood of V. So that means that no matter what you do, in order to cover here all these edges, you need always to have at least delta over omega minus 1 many colors. Otherwise, you cannot find a valid coloring of this click cover, right? Because okay, so the idea is this is certainly a lower bound on the click covering index, the maximum degree over the size of the largest click minus 1. And these are, of course, very classical parameters. We understand very precisely how the maximum degree behaves in the random graph and how the largest click behave. So up to 1 plus little O of 1, this expression here is just, well, the maximum degree is something like n times p, and the largest click is size roughly 2 times log n to the base 1 over p. Okay, and for constant p, this exactly reduces to np divided by log n. Okay, and I should mention that in fact, this lower bound here, even if p tends to 1, is qualitatively up to constant factors best possible. But for this talk here, the main focus is on constant p. Okay, so let's maybe. So if there are no questions here about what the conjecture is, let me maybe move on to our main result. So the main result is that we basically prove this conjecture of Ferdi and Cantor. So here, remember, we switched to this click covering index of GMP. So we show that with high probability, this is of order n over log n for constant p. I hope that the paper will appear in archive next week or maybe the week afterwards. So this in particular implies this Prague dimension result, as we discussed, because the Prague dimension of GMP corresponds to the click covering index of GN1 minus p. There's two noteworthy things here. So we have a bunch of extensions of this result, which I'll not cover too much here. So for this particular result about this click covering index, we also can figure out what the order of magnitude is when p goes to 0 as a function of n, so in the sparse case. And we also can strengthen this result here in the sense that when we looked at this property, we were always looking at click edge coverings. So that means that every edge of your graph needs to be contained in at least one click. And in the context of various hypergraph problems and so on, it's well known that covering problems usually tend to be a little bit easier than packing problems, because this constraint of containing being contained in at least one click is a little bit easier to satisfy than this packing constraint that you need to be contained in exactly one click. Nevertheless, here in this context, we can also prove a packing variant of this problem. So instead of click edge coverings, we look at edge packings. Let me maybe make one more remark here. So one thing that we see here from this lower bound argument is somehow to get to the fact that this bound here is n over log n. If you look at this lower bound construction, it basically tells you that you need to use in your click covering lots and lots of large cliques, lots of cliques of size something like log n. Otherwise, you cannot prove this kind of bound here of size n over log n. So we need to use lots and lots of these pretty large cliques of size order log n, and this causes some technical difficulties, in particular when we try to color these cliques. As many standard results for covering or the chromatic index of hypergraphs, they're valid for edge uniformities of constant size, not when these edges grow as a function of n. I think now that we've seen what the basic quantity is, the conjecture, and the main result, I think it's good to quickly think about what is the motivation or the context here. On some of these things I've already touched. So on the one hand, we want to, this falls into this general random graphs paradigm that we take some graph parameter that we don't understand very well, and we study it for random graphs to get the basic understanding of what's going on. In particular here, if you think about what's happening for p equals to 1/2, for constant edge probability p equals to 1/2, what you get is a uniform distribution over all n vertex graphs. So if you can prove that with high probability, the parameter that you're interested in is of a certain order for gn 1/2, what you actually shown is that for almost all graphs satisfy this property. So in particular, we know that almost all graphs have Prague dimension n over log n, which is significantly smaller than the worst case bound you can get, which would be of order n. Okay, so this is this random graphs perspective. I think the second theme where this topic nicely fits in is in this general trend of covering and decomposition problems, where you want to decompose the edges into smaller parts. And here the extra twist is that for this problem, you need to kind of decompose or cover the edge set using objects that are not of constant size, like cliques of constant size, but you really need to use very large cliques or objects, which is maybe an interesting twist on the existing problems. Also, let me mention here that somehow this idea here of decomposing into these cliques is kind of the opposite the way you think about this dimension, right? In dimension, you ask yourselves, okay, what are the smallest possible units and how can I embed my graph into the product of these one-dimensional things? And somehow when you think of it from the covering or decomposition perspective, you think, okay, let's take this big complicated thing and decompose it into smaller things. These are, seem to be two related viewpoints on very related aspects. And finally, one thing that I like here in particular about this problem, it's, as we'll see, it can be solved using some random greedy paradigm. And so basically, we want to construct certain things in some random greedy way. And the nice thing that happens here is that we are going to use both of the major themes in this area. One is where you construct your objects step by step. And the other is where you use this semi-random nibble type approach, where you always construct your objects by using large chunks or taking large chunks of your object at a time. And in each case, the usage of the specific technique will have some technical advantage compared to the other. So in some sense, we're using here the best of the two worlds of the random greedy paradigm. Okay. Let me mention that some related parameters have been studied before. So for this, it's again useful to think of this click covering index in this form that you minimize over all possible click coverings of the chromatic index. And once you take that perspective, now you can imagine that in here you can put all kinds of other parameters of interest, right? So perhaps the most natural one is that you want to look at the size. Okay, you want to minimize the size of your click edge covering. So this was some result by Fries and Reed from 1995, where they showed that the minimum size of a click edge covering is of order n squared over log n squared with high probability. So instead of size, you can also look at the degree. So in other words, what you're thinking about is, okay, what is the maximum number of clicks that one vertex is contained in? This is really also very closely related to the chromatic index, right? Because the chromatic index has to be at least this maximum degree. And so Freddy and Cantor in 2018 showed that this maximum degree is of order n over log n by reusing some ideas here from this Fries-Reed paper. They managed to deduce this. Let me mention that our result also extends to these other notions here of size and degree. So in particular, we can also prove some versions of these results when p goes to 0. And we can also replace here the click covering constraint by a click packing constraint. So we need to take really a decomposition of the edge set into clicks. In fact, the situation perhaps is quite interesting. Here, it turns out that we can construct one click covering of G, of the random graph GMP, or one click partition, which actually gives all these bounds. So we can show that there's in some sense some kind of well, let's say weakly pseudo-random click covering, which has this size where the degree is at most this, and where the chromatic index is at most this. So so there's this one kind of pseudo-random like click covering that we can construct, which gives the up to constant factors the right upper bound for all these parameters of interest, and maybe there are also other parameters that one can study here. Okay, this would be so an excellent time for questions.
Lutz, I noticed you wrote Joel here. You wrote theta on everything. Is it correct that you do not know with a proof what the correct constant is?
Okay, so the situation is like this. We know that it would be, for example, here np over log to the base 1 over pn. The only thing that we need to restrict here is that we want to avoid the case when p goes to 1. So here you have some constraint, maybe p is at most 1 minus gamma. But if you have p at most 1 minus gamma, then this here is an honest theta, where this constant here might depend on this gamma, but not on p. So
maybe I didn't say the question correctly. Okay. Fixed p equals a half. Do you know the correct constant? You say it's np over log base 2.
I see.
Yeah.
Yeah. So the correct constant, that's what I'll mention later. That's still that's open.
Okay. Thank you.
The situation seems quite delicate. As I'll show later, this lower bound here, one might believe that it's close to the truth, but one can do better. So,
okay.
Yeah. Okay. More questions?
Chart is empty. So.
Okay. So let me maybe then say a few words here about the proof strategy. So as I already mentioned, the proof strategy will come in two parts. The one part will be to construct the click covering, and the other one will then be to color it. And so each time we're going to use some random greedy paradigm. And so in the first case, we're going to use some semi-random nibble type argument to construct this click edge covering. So each time we're going to sample some random clicks from the graph and put them into our collection, and we repeat this many times. And here we use this semi-random approach. And from the technical perspective, the advantage of using semi-random here is that somehow once you start taking out these clicks from your graph, using the semi-random approach, it's easier to show that the remaining leftover graph has very nice properties. In particular, that when you look at the click distribution, that the total number of clicks is roughly what it still should be, that the number of clicks per vertex is what it should be, the number of clicks per edge is what it should be, and so on and so forth. Okay. So for the purpose of what I'm going to discuss in the talk today, this first part here has some strong similarities with the argument of Fries and Reed, who constructed, who were looking at the size of the click edge covering. But when you look at the, instead of coverings, you look at packings, then you need to modify this part further to make sure that really everything is disjoint. Okay, so we first find this click edge covering using the semi-random nibble type argument. And then basically we want to color these clicks here in some greedy fashion, thinking of these clicks really as this collection of clicks. So each of these chunks that we take out as some small hypergraph with vertex set 1 up to n, and each click corresponds to an edge in your hypergraph. And then we want to edge color this hypergraph using some random greedy algorithm. And so the way we're going to do this, I'm going to expand on this later, but the idea is basically we're just going to use disjoint colors for each of these sets that we pull out using this random greedy algorithm. And although we sum over a huge number of such different sets here, we can still control the overall contribution and get this upper bound of form n over log n. The advantage why we use here some random greedy algorithm instead of semi-random greedy algorithm is because somehow using random greedy algorithm here, it's easier to ensure that you really cover, that you really color all of the clicks. If you use here some semi-random approach, you would need to take a little bit more care what happens when certain things clash and so on and so forth to really ensure that you color all the clicks. And if you directly use this random greedy approach, which colors one click at a time, this is easier to guarantee. Okay, so this is the high-level proof strategy. And let me maybe say one or two words here more about it. Okay, so the first part is that we want to decompose basically the edge set into clicks. And so the natural approach that we do here is we're just going to gradually sparsify the random graph GNP. So the idea is we start off with GNP, let's just denote it by G0. Then we're going to take out some clicks of this graph G0. Basically, we randomly delete certain clicks of size order log n. So there's some parameter fine-tuning involved here, but the idea is that we each time delete a bunch of clicks which cover a reasonable proportion of the edges of the current graph, so that as we move along here, this chain, the graph gets sparser and sparser. Okay, so we always take out certain clicks, make the graph sparser and sparser. And then similar to what we know, for example, from the normal chromatic number coloring algorithm by Bira-Bolobash, once the graph here at the end is sufficiently sparse, then we can just do something very basic with all the remaining edges. So here, we're basically crucially exploiting the fact that in this problem of click coverings and click decompositions, nobody forces us to always use just clicks of a big size. Once the graph is sufficiently sparse, we can just put all the remaining edges here into our click cover. That's fine. Okay, so we gradually sparsify the random graph G and P by taking out cliques of very large size. And this procedure here on a technical level is facilitated by the fact that you can show that as you delete more and more edges here, in some sense the remaining graph still is pseudo-random, in a sense that you can show that GI looks like some random graph G and PI with some decreasing probabilities. In this case, here when we look at click coverings similar to freeze and read, this will be exponentially decaying. So the graph PI looks, the graph after I steps looks roughly like a random graph G and PI, where PI is the original P multiplied by e to the minus I. Okay, so if you do this many steps, then your edge probability gradually shrinks down. And to really show this, you need to add some extra bells and whistles to this process. So it's not just enough to delete clicks, or rather, I don't know how to prove this just by deleting clicks. Each time what we do here is we remove some extra edges from the graph, which intuitively balances out certain random variations that otherwise would happen. But this is some technical point. I don't want to go too much into detail here. The key idea really is that we just find these clicks by just selecting random clicks from the current graph. And so the idea is we select random clicks from a graph that looks pseudo-random-like, so the collection that you take out should have all kinds of nice properties. Okay, so this is this first part of the strategy. How do we find our click covering? And once we have this click covering of the edges, now the question is how to analyze that. So in this case, we're interested in the chromatic index here of this click covering, but in principle we could also look at the size or the maximum degree, all these other quantities that we mentioned. And so for the click covering index, well, because it's the minimum of the chromatic index over all possible click coverings, it's certainly bounded by the chromatic index of this particular click covering that we constructed here. Now, for each of these sets of clicks that we take out, we use different colors. So that's how we can bound this here by the sum of, say, the first I terms plus the chromatic index of the last collection that we take out. And so now the idea is that we want to bound each of these individual terms, potentially using some random greedy approach. So some things are easy here. So because remember, we sparsify the graph until the final graph I promised you is relatively sparse. Okay, and then we just took all the edges of this graph and put it in the last collection. So it means that in particular, if you look at the chromatic index here of the last one, that's fairly easy to control, right? Because now we're just looking at the coloring of edges. So this is certainly at most 2 times the maximum degree here in this remaining graph. Or you could do better by saying, okay, I can use Wiesing's theorem, and it would be at most delta +1. But here we don't care about constant factors, so we can just be generous and say, okay, this is certainly at most twice the maximum degree. Okay, so, and if you believe what I claimed up here, that the graph GI looks like some random graph G and P, then you would see that this final guy here contributes at most this, right? Because the PI was PI is equal to P to the e to the minus I. So here, this would be the contribution from this final term. And now you see that if you can make this I up here, the number of iterations sufficiently large, something like some big constant times log n, say, then this term here will be significantly smaller than what we're aiming at. So this final term is surely fine. So the main question is, what can we do here with these first terms? Okay, so because here we're looking at the chromatic index of some collection of cliques, and the point is here, the main challenge is that we need to color this hypergraph where each edge is extremely large, can be up to size log n. So in the best of all worlds, what could we hope for? Okay, so there's this very nice chromatic index result by Pippinger and Spencer from 1989, which says that some hypergraphs, which are nice in the sense that they're approximately regular and don't have too large codegree, that you can actually color them, or the chromatic index is at most 1 plus epsilon times the maximum degree in this hypergraph. Okay, so their result, as I'll elaborate more on in the next slide, does not apply here, because this collection CI does not has edges of very large uniformity up to log n, whereas their result only applies to edge uniformities of constant size. Okay, but still, let's maybe hope for the best. Let's dream that maybe we can prove something like this. Maybe we can also bound this by some constant term multiplied by the maximum degree of this hypergraph. So let's just pretend that we could do this. So if you do this and you do the calculations, then you'll see that you can bound this first term here by some sum. Okay, so the main point here is that what you have here is that this is something like n times pi divided by something like log n based to the base 1 over pi. The main message here is just because these PIs decay so fast, because these edge probabilities, these PIs decay so fast, basically this entire sum, if you do the calculus, is dominated by the first few terms. Okay, and so the first few terms are exactly of the form that we want. It's n times p over log n to the base 1 over p. Okay, so but this is all just a matter of optimizing the parameters. The main point really is that we want to establish here our dream statement that the chromatic index of these guys can be bounded basically by a constant times the maximum degree. And if this would be true, then it turns out that indeed the upper bound that you get here on this click covering index is what you want. It's of order np divided by log n to the base 1 over p. Okay, so the plan for the remainder of the talk is to say something more here about this point, how we can achieve this dream statement. But otherwise, this would be a good time to ask questions about this the proof strategy, the high-level proof strategy that we use here. Otherwise, so far. Okay. So what was the problem here with our dream statement? So the dream statement is that it doesn't work because these clicks have this large size up to log n. Okay, so let me maybe, as a reminder, state once this Pippinger-Spencer theorem in slightly informal way, but all the gist is here. So I think of it as like a replacement of Biesing for normal graphs. So Biesing's theorem tells us that if you look at the chromatic index of a graph, it's at most delta plus 1. And this result of Pippinger and Spencer tells us that for certain hypergraphs, you can get something similar in the sense that the chromatic index is at most 1 plus epsilon times the maximum degree, where you can make epsilon arbitrarily small. And their result applies to any hypergraph H, which satisfies a bunch of properties. In this case, the uniformity, the size of each edge should be constant, the graph should be approximately regular, and the codegree should be much smaller than the degree. Okay, so once you have this, then you can get this kind of result. And so the interesting thing here perhaps is that if you look at this collection of click CI, it actually satisfies these last 2 points. So it turns out you can prove that it's approximately regular and has much smaller codegree. So the only barrier here is this K uniformity bound in this Pippinger-Spencer result. And I'm pretty sure that if you look into the proof of Pippinger-Spencer or some other proofs that have emerged since now, you can surely do something here with this uniformity. Maybe you can improve this a little bit. It's not just order 1, but at some rate growing to infinity. But to go all the way up to log n will be surely very challenging. So the idea that we use here to overcome this problem is to say, look, what this Pippinger-Spencer result does is a deterministic result. It holds for any hypergraph H. Okay, so but what we're doing here the setup is slightly different, right? If you remember, where did the CIs come from? Well, we looked at some graph GI, and then we randomly sampled clicks from there to get the CIs. Okay. So in other words, we still potentially can exploit the fact that this CI is actually generated in a random way. We have a bunch of clicks in our graph, and we select some of them at random. Okay, and this is what we should exploit. We should exploit the randomness in our proof environment to do better. Okay, and this is the key point. I'll make a more precise statement on the next slide. The key point is by realizing, or by really using crucially the fact that this CI is chosen at random, we can do better. We can effectively relax here this constraint from edge uniformities of constant size to also allow for uniformities that go all the way up to log n. Okay, so again, the key point is their result holds in deterministic setting. It's true for any hypergraph, but in our setting, we have still some randomness that we can work with, which allows us to do better. Okay. Okay, so what is the statement that we can prove to this effect? Let me maybe give you some, or let me maybe say one word, why sometimes some of this uniformity here is sometimes a little bit tricky for these results of Pippinger or Spencer type and so on. So in many of these cases, the way these results are proved is that you cover, or that you color almost all of the edges of your hypergraph using maybe some random greedy approach or something like that. And then you deal with the remaining edges, say some epsilon fraction of the edges, you deal in some very crude way. So in particular, one way, one very trivial upper bound of the chromatic index is at most k times the maximum degree of a hypergraph. So if you can ensure that after looking at most of the edges of your hypergraph H, the residual degree is very small, say at most delta times the original maximum degree, then by appropriately choosing delta sufficiently small, you can make things work. But as you can see, how you choose delta and so on depends crucially here on the edge uniformity k, if you do such a crude argument, where you just want to use some trivial argument for the last few edges. And so that's one of the reasons why these results here are harder to control for constant edge uniformities. But that's maybe just a small digression. Let me return here to how does the chromatic index result that we can prove look like. As I said, I hope that we have this on archive in a week or two. So here's basically the assumptions that we're looking at here. So we're looking at some hypergraph H, which is k uniform and has n vertices. And so here we have three conditions. So we have one condition on the edge uniformity. So we want to ensure that the edge uniformity is between 2 and some constant b times log n. Okay, so this is good. Here we can allow for very large edge uniformities. Then we want some very strong form of approximate regularity and small codegree. So by very strong approximately regular, I mean something like this: that the degree of each vertex is up to some polynomial error term equal to d. Okay, so it's 1 plus minus n to the minus sigma for some constant sigma times d. So it's very, very regular. And in comparison to the degree, again, the codegree between any two vertices u and v should be significantly smaller. In this case, some polynomial factor smaller, n to the minus sigma times d. Okay. And then what is the object that we want to look at? Well, we want to look at some random subhypergraph of H. So in this case, we want to sample m edges from the original hypergraph H, where m here in this case should be, well, not too small, at least n to the 1 plus sigma. And here, let's not sample all the edges of our graph H, but significantly less than all of the edges. Okay. So once we're working in this regime, then we can prove that with high probability, the chromatic index of this random subhypergraph is at most 1 plus delta times the maximum degree of this hypergraph HM. And here, which might be perhaps a little bit non-standard, I can give you some explicit expression for what delta works here. So up to constant factors, delta will be basically this constant b from the edge uniformity divided by sigma, which comes here from the error term. Okay, this might look like a strange way of formulating the result, but it has some advantage to get some explicit dependencies between the things. as I'll mention in a moment. So the main point here is, I should say that we didn't try to optimize too much any of these conditions here. Our main goal was here to allow to go all the way up to log n, though there is some connection, at least for our proof, between the fact that here we have a polynomial error term n to the minus sigma, and the fact that here we can go all the way up to log n. There's some connection between that. Let me comment on this non-standard fact that here I give you some explicit delta. How does that relate to these previous results? Okay, so because in the end we want to say something about the chromatic index of HM, and by formulating this delta explicitly, we get two kind of results effectively. So one range is when the edges are very small, when the uniformities are little o of log n. Okay, what that means is that I can choose an arbitrary small b up here for the edge uniformity. This constant b I can make arbitrary small. So in particular, this means that this 1 plus delta, I can just think of it as 1 plus epsilon. Okay, because I can choose any b up here that I want, and then I get really like a Pippinger-Spencer type result. This 1 plus epsilon times the maximum degree. Okay. On the other hand, if we want to work like in our case with edge uniformities all the way up to log n, then what you see here is that this delta term, it becomes a constant, right? So we have the sigma term here from the error term, that's a constant, and the b will also be a constant if k can be all the way up to log n. So in other words, this 1 plus delta term becomes an order 1 term. And this is exactly what we will apply in our setting. Okay, so in our setting, we want to allow for having these cliques of all those size all the way up to log n. And then we will apply this result here, which tells us, okay, we can bound the chromatic index by a constant times the maximum degree. And if you go back, then I promised you that, okay, if you can bound this by some constant times the maximum degree, then it's enough to push through the entire calculation and make everything work. Okay, so these are these two views on this result, enabled by the fact that we can get an explicit dependence here on what delta term works. So the proof of this result is algorithmic. Basically, we show that the natural random greedy algorithm using at most 1 plus delta times km over n colors works. So this is really the most natural algorithm you can imagine. You just look at the edges one by one, and each time when you look at an edge, you just select a random color that is available for this particular edge, and then you prove that with high probability your algorithm will be successful in coloring these random edges. Note that we're really using this kind of double randomness here. We're interested really in this random hypergraph HM, but in order to color it, we use a random algorithm, randomized algorithm that succeeds with probability tending to 1. Okay, so we use a randomized algorithm to color these random edges. The proof is, there are two things I should mention. So on one hand, so this random greedy algorithm that differs from the one that Pippinger and Spencer used, it's a little bit more in the spirit of some algorithm that was in spirit used by Kahn in the mid-90s for list coloring. He did not use the random greedy variant, but he used a semi-random variant, which also later used by Molloy and Reed in some other context. And this random greedy algorithm was also analyzed to to look at the chromatic index of a random k-uniform hypergraph. And so this was some work by Valentas, Kurauskas, and Rybarczyk. So they used it to analyze the situation for random k-uniform hypergraphs, which is something like this, when here the hypergraph you're looking at up here would be the complete k-uniform hypergraph. Okay, so the proof here is based on the differential equation method. So this is some powerful technique which allows you using martingale techniques to show that various random variables behave the way they should be, and you can predict the way they behave using differential equations. So this is a very technical proof. Well, let me say it like this: the method is very technical, but the actual proof that we have here for analyzing this algorithm is really nice. So I think I think personally, for all the differential equation proofs that I've written, this might be the neatest one. So maybe once this is an archive, this is a good paper to learn how this method works. Here, in this case, a lot of nice things happen which simplify several of the technicalities. Okay, again, this will be a good question to ask, time to ask questions about this particular result. Okay. Let me maybe move on to this open problem. In some sense, Joel had already basically asked this question earlier. So the question here is, what about the asymptotics of this, for example, here, this click covering index. So we're interested in the minimum color needed to color some click covering of the edges. So what do we know? So we know that it behaves like order, with high probabilities of order n over log n for constant p. Then there's we had this fairly simple lower bound observation, which was just based on the fact, okay, once we know the degree of a vertex and we know how much the maximum degree is, that tells us that in any click covering, a vertex must be in at least this many clicks, and hence to properly color your covering, you need at least this many colors, okay? So maybe once you see this lower bound and you remember how we proved the upper bound, which gives kind of some similar expression here also in this hidden theta notation, then you might be willing to guess that maybe the lower bound is not too bad. Maybe the lower bound is not too bad. But at least for constant p, the situation is more complicated. So it turns out that you can do better. So you can improve this simple lower bound up here using some other argument. Basically, what we do here is we use these global statistics, right? Maximum degree and largest click, to argue about how many clicks this vertex must be in. But there's some kind of more global argument that you can do. You can do basically a union bound over all possible click edge coverings, where each vertex is contained in fewer than this many clicks. And if you do that, you see that there are so few such click edge covering where each vertex is contained in less than so many clicks, that you can show that the probability that random graph admits such a click covering goes to 0. Okay, so the main message is this lower bound is not correct. You can do a little bit better. And just that you give a flavor of what's going on, so we can get basically this expression, we can squeeze in some extra term 1 plus f of p, where f of p is strictly positive for p between 0 and 1. So this p is also has the limiting behavior. If p goes to 0, then this f of p goes to 0, so the improvement you get goes away. If p goes to 1, then this f of p actually tends to infinity. And that's the reason why in our result earlier I mentioned we sometimes exclude the case when p tends to 1, simply because this bound that we get here is no longer true. For p equals to 1/2, it's maybe nice to know that this extra improvement here gives an extra factor of 2. And besides using this union bound argument, it's not clear to me if this potentially has some combinatorial explanation, or if there's maybe some other guess as to what the correct order of magnitude would be. I think it would be nice to understand the asymptotics. Okay, let me maybe summarize. So what was going on? So we looked at this notion of dimension for random graphs. And we showed that typically the Prague dimension is of order n over log n for constant p. In particular, this implies that for almost all graphs, the Prague dimension is of order n over log n. This particularly verifies this conjecture of Furedi and Cantor. The proof uses this combination of semi-random greedy algorithm and random greedy algorithm, each time using the best of its two features. One new tool that we introduced here, which I hope will also have applications beyond this particular one, is that we can bound somehow the chromatic index of random subhypergraphs where the edge sizes are very large, where you do not just restrict to edges of constant size, but all the way up to logarithmic size. And really, I want to finish with these two questions, which I think would be nice to understand. One is what we already discussed. What is the asymptotics of this Prague dimension for constant P? What can we say about the leading constant? And another thing, which we didn't look into too much, is what can we say about the Prague dimension, the sparse case, when this edge probability P goes to 0? Note that here I'm saying we're looking at the sparse case, but if you remember, the Prague dimension was defined in terms of the complement of the click covering index. So in reality, the sparse case of the Prague dimension corresponds to the super dense case of this click covering index, where the edge probability tends to 1. And in that case, the way we get our upper bound, those tools break down. So we didn't look too much into that, but maybe there's also something interesting to be seen there. And with that, I'll stop. Thank you very much for your attention.
Thank you very much. So let us thank the speaker. Okay, maybe some questions. We have some time.
Yes, I have a question, Dimitri.
Yes, please.
Yeah. So what? Let me just take P equals a half. So what size cliques are you using? Cliques of near maximal size, 2 log n or 1 log n? What size cliques are you using in this construction?
So so in this construction, let's see. So we use some cliques of size initially here of, instead of 2 log n to base 2, we use something like maybe 1/20 times log to the base 2n. But this 1/20 you can improve, but I think you cannot do, our proof breaks down for technical reasons. I think you cannot use cliques of size larger than maybe 1 minus epsilon or 1/2 times log n, something like that. The reason is that otherwise I don't know how to keep control over them, because what we're doing here is we're saying after we take them out, we again want to make sure that all the cliques, if you look at each vertex, edge, and so on, that you have the correct number of extension counts. And if you go all the way to those of maximal size, I don't know how to iteratively control those quantities. So it's so our argument certainly cannot use these cliques of size 2 log n. It needs to use some constant smaller.
Okay. Yeah,
So,
I mean, there's a lot of work. I see Annika's here with many people, including Annika on using cliques that are very close to the maximal size, indeed at the maximal size. But here, I mean, if you had cliques of size 1.999 log n, I mean, you know you have quite a few of them. But I can see your explanation that other problems come up.
I mean, I think the interesting thing is already one thing we put in the paper, but I didn't mention here, is even just determining. Wait, let me go back here. Even the size here. This is also open to figure out what the correct answer there is. And there again, one is kind of tempted to say that this n choose 2 times p divided by the largest clique choose 2, that should be the correct answer. So
Right.
because somehow if you look, instead of cliques of largest size, look at cliques of size, largest size minus 10,000. Then every edge should be in a humongous number of such cliques, right? So you would hope that maybe you can find an edge disjoint collection just using those guys. But again, this will not give you the correct answer. There's a similar argument to, there's a similar argument to this construction here, where if you do a union bound over all possible clique coverings, you can do better. You can do better than this bound that you would otherwise expect of something like n choose 2p over omega 2. You can do better. You can show a better lower bound. You could squeeze it against some extra factor. So yeah, I think understanding the combinatorial structure of these good clique coverings and so on, that seems to be a challenge that we don't understand yet well enough. But
Okay.
yeah,
Okay, thank you.
Okay, any more questions? I don't see anything in the chat. Okay, so let us thank Lutz once again.
Thank you.
Okay.